Yesterday we discussed about importance of selecting the sampling frequency in case of A to D conversion. If you remember, more the sampling frequency, good is our conversion from analog to digital, right? So the importance of sampling frequency, we saw that the sampling frequency should be at least twice that of the analog signal frequency, right? We call it as Nyquist criterion. Okay. So let us move further. We'll see three types of analog to digital converters. First is successive approximation type ADC. Then we have a ramp ADC. We have then flash or direct type of ADC. We'll go to the first type, that is successive approximation type ADC. Please have a paper and pen, friends, so that we can understand the things better quickly. I'll try to explain to you. Now, as you can see in the diagram, you have one operational amplifier here, which is acting as a comparator. What it does, it compares the two signals, my set signal and my generated signal, and after comparison, it gives out some signal. So op-amp as a comparator is used here, and as you can see here, there is one logic gate. In this case, it will be OR gate. Then you have the clock. Just now we talked about for A to D conversion, I should have some reference clock which is generating the pulses with my desired frequency, isn't it? Which will be helping me in chopping down the analog voltage. Okay, so this is the clock, and the gate allows either the signal from the clock or from the op-amp, right? And then the output from the gate is given to a 4-bit storage register. The output from the gate is given to 4-bit storage register. And whatever is the digital output, that is connected back to my D2A converter. It's a 4-bit register and 4-bit D2A converter. All these digits are connected to a D2A converter, which will convert this digital signal into analog signal, and then this analog signal is fed back to my comparator. Please be attentive. Now, listen to me very carefully. This is the analog signal that I am getting from my sensor transducer. I want to convert this analog signal into digital form. This is what is my requirement. Please be attentive. The analog signal received from the sensor transducer is to be converted into digital output. Now, this digital output will be given further to either my microprocessor or microcontroller, which will be further processing the signal. As we know, microprocessor and microcontrollers can process only digital signal. So this digital output will be given to my microprocessor or a controller for further processing, and thereafter it will go to my actuator. Okay, this is how is the arrangement. Okay. Now the analog signal that I want to convert is given to my op-amp comparator, and it is given to the gate. Now what I do? Now initially this input from the op-amp is closed, right? So as I said, it is OR sort of a gate. So initially the gate will allow the signal from clock only. Remember, I'm not receiving any signal from the sensor transducer. I'm receiving signal right from clock. What the clock is doing? Clock is generating the pulses. Now, how I'm going to select the pulses? Based on, see, I know, suppose the analog voltage is corresponding to, say, 8 volts. 8 volt, I know, just to understand the concept, 8 volt is to be converted into digital signal. And as we know, it will be 1000. You will come to know how it is. Okay. So this 8 volt, what I do is I select the clocking frequency just below the value of my input analog signal, little less than the input analog signal. So the clock will generate the pulses at a defined rate. Those pulses, this gate will allow those pulses to go to the register, 4-bit register, and those pulses will be digitized straight away. Okay, so let us say those pulses correspond to voltage of, let us say, 7.5 volt. And that digital, because it is a digital signal I am giving, okay, this digital known signal I am generating through the clock, and I am giving it to the register or the counter. So a digital number will be generated corresponding to 7.5 volts. Now this digital, the 4-bit digit, will be given to my D2A converter. So that D2A converter will convert my digital signal corresponding to 7.5 volt into analog signal. Understanding it? I'll repeat it. Just be attentive. I'm not taking any signal from the transducer presently. I'm taking signal. Please be attentive. I'm taking signal only from my clock, whose frequency and whose amplitude I can adjust. So I will generate, initially I'll generate a voltage pulse corresponding to a frequency which corresponds to a digit, to a digital number or a binary number, whose value will be slightly less than the value that I'm going to count. As an example, what I said, I know that analog signal is corresponding to 8 volt DC. So I'll select the clock frequency in such a way that the digital signal that I'll be generating will be of lesser value, maybe 7.5 volt value, and that in digital form I'm generating through my clock. So the gate will allow this frequency, this pulses to my digital counter or 4-bit register, and that digital signal corresponding to 7.5 volt will be generated here. And that digital signal is fed back to a D2A converter. So what this D2A converter will do, this digital signal corresponding to 7.5 volt will be converted into analog form. What will be its analog form? It will be 7.5 volts, because I know it. 7.5 volt will be fed to the op-amp. Now, what is the input signal? Input signal is 8 volt. What is the feedback signal? It is 7.5. Okay, so this cycle, still the gate will not allow the signal from the op-amp. Till what time? Till this feedback signal, I'll keep on generating the digital signal. And 7.5 volts, 7.6 volts, 7.8 volts, 7.9 volts. Accordingly, this signal will be fed here and will be constantly compared with the input analog signal. Presently, as I said, it is 8. So till I reach this generated signal, this is my generated signal. Till my generated signal, which is converted into analog form, becomes equal to or slightly more, equal to or slightly more than the analog signal, till that time, this gate will not be opened. Okay, once the signal becomes equal to or greater than the analog signal, this gate will be opened. Now, once this gate is opened, this gate is closed. So the clock will be stopped, or the clock gate is closed. And what will happen? Through this gate, the analog signal that will be converted directly into my digital form. And that moment, that will be my true representation of my analog signal. But till that time, what was happening? Please be attentive. What was happening? This gate was closed. I am not receiving any analog signal. What I am receiving? I am receiving a pulse signal from a clock, and the gate is allowing only that pulse signal, and it is showing the digital value of that, of which I already know the digital value. Actually, the trick is that the value that I am generating and the equivalent value of that analog voltage of the digital signal that I am generating, that will be compared here. As I said, if I want to measure voltage of 8 volts, what I'll be doing? I'll be starting off with the clock frequency and the digital binary number, which corresponds to voltage of 7.5 volts. Okay, so that 7.5 volt analog signal will be compared with my 8 volt input signal, right? And this cycle, in each successive iteration, I'll be slowly increasing this binary number. 7.5 volts, 7.6 volts, 7.8 volts, and accordingly the binary numbers will be generated. Those binary numbers will be fed back through my D2A converter, and those will be fed back to my op-amp. And slowly, this gap between 8 volt and 7.6 volt feedback signal, 7.9 volt, one moment it will be equal to 8 volt. And once it becomes equal to 8 volt, this gate will be opened and this clock gate will be closed. So that signal will be converted into my digital register. That will be shown on my digital register. That will be the true representation of my analog input signal. This is how this successive approximation type A to D converter works. Now, what is the important part? There is a lot of task that is to be done. I need to every time I need to have the reference value. What is the digital signal which is nearer to my analog signal value? So this kind of trial and error and frequent iterations are to be done. Remember, though I'm telling you the iterations in one by one fashion, but this clocking frequency is of the tune of microseconds. So we don't even realize when this successive approximation has happened. The sample and hold circuit will directly show me the analog signal converted into digital signal form. So it will not show me slowly the counter is increasing. No, because this clocking frequency is so high. It is of the tune of microseconds. In some cases, it is in nanoseconds. So these iterations take place very fast. And the conversion that I see within the blink of the eye, I'll get the digital conversion, which I'm telling to you that after some iterations, the feedback value, when it becomes equal to my analog signal, then the gate opens and then I have the digital representation. So I'm verbally telling you in a slow fashion. Practically, this counter works very fast and you get the digital representation of my analog signal. This is how this successive approximation type A to D converter works. Quickly, you try to draw the sketch. Well, all these things, as I said, are from Bolton. Bolton will be your good book for reference. Okay, there are other books, but this is very precise to the point and the sketches are self-explanatory. And as it is written by a mechanical engineer, obviously, he knows the depth to which we should know. We need not get into the details of all the logic circuit design. No, we should at least know how this successive approximation type ADC works. Okay, let us quickly see the verbal part or the theoretical description. This successive approximation A to D converter. So I'll read it slowly. Please be attentive. Successive approximation is the most commonly used method. Initially, the gate allows voltage pulses from clock only. Voltage pulses from clock only. This gate is closed, or this end is, this port is closed. Initially, gate allows voltage pulses from clock only. A voltage is generated by a clock emitting a regular sequence of pulses which are counted in a binary manner. Generating the voltage pulses through a clock which are counted in a binary manner. The resulting binary word converted into this resulting binary word is converted into analog voltage by a D2A converter. Refer back the sketch. This resulting binary word is given to a D2A converter. So this binary number is converted into analog signal. The resulting binary word converted into an analog voltage by a DAC. The voltage rises in steps in each iteration and is compared with the analog input voltage from the sensor. Right? So this comparison constantly happens. Iteratively, it happens. When the clock generated voltage, equals and crosses the input analog voltage, when the clock generated voltage equals and crosses the input analog voltage, gate is closed from the pulses from the clock. And the output from the counter at that time is then the digital representation of the analog voltage. So when the clock generated voltage equals and crosses, this port is closed and this port is open. So at that time, whatever the counter is showing, that will be the representation of my analog signal, unknown analog signal. When the clock generated voltage equals and crosses the input analog voltage, gate is closed for the pulses from the clock, and the output from the counter at that time is then a digital representation of the analog voltage. In successive approximation, the most significant bit, so what is the leftmost bit, corresponding to a value little less than the analog voltage is selected. I told you the analog value, if I am going to measure 8 volt, I'll be starting with a digital word or the digital value corresponding to maybe 7.5 volt, maybe 7.6 volts. It all depends on within how many iterations I want to reach out the unknown value. So in successive approximation, the MSB corresponding to a value little less than the analog voltage is selected. Then successive lesser bits are added, for which the total does not exceed the analog value. Right? So let us say, for example, I want to measure 9 volt, let us say. Unknown value is 9 volt. So I'll start with 8 volt. What is the binary number correspond to 8 volt? As we discussed in the previous classes. So 4-bit word, if you consider, the binary representation for 8 volt is 1000. Okay. I want to measure 9 volt, let us say. So what I'll do next? I'll go to next significant bit. So 1000 corresponds to 2 to the power 3 corresponds to 8, 2 to the power 2 corresponds to 4, 2 to the power 1 corresponds to 2, and 2 to the power 0 corresponds to value 1. Hopefully, take a piece of paper, write 1000. 1 corresponds to the most significant digit corresponds to 2 to the power 3. The next digit corresponds to 2 to the power 2. The next digit corresponds to 2 to the power 1. And the last digit corresponds to 2 to the power 0. Okay. So what I'll do next, I have started off with 2 to the power 3 and remaining are 0. Right? So 2 to the power 3 corresponds to 1000. So in the next iteration, what I'll do, if I use the next significant digit, let us say 4. So 8 plus 4 will make it 12. So it is not useful. So I need to keep second significant digit as 0 only. So I don't want to use 2 to the power 2. Can I use 2 to the power 1? 2 to the power 1 is 2. So 8 plus 2, 10. No, it is not useful. So that will also be 0. Now the last digit, 2 to the power 0. Is it 2 to the power 0 corresponds to 1. So the next digit that I'll be generating is 1001 corresponds to 8 plus 1, right? 9. So number of steps I can increase. Okay. So the next, so 9 voltage will be achieved by 8 plus 0 plus 0 plus 1, isn't it? So the binary number corresponding to that is 1001. Right. So this signal I'll be generating through a clock, and that signal will be, that binary number will be converted by my D2A converter into analog signal. Then it will be compared. Okay, when it is equal to that, then the analog signal, the gate will be opened for this analog signal. The clock gate will be closed, and that 9 volt will be converted into digital form. That will be my representation, binary representation or digital representation of my 9 volt signal. Okay, so then successive lesser bits are added, for which the total does not exceed the analog value. Because each of the bits in the word is tried in sequence with an n-bit word, in our case it was 4-bit word, n-bit word, it only takes n steps. In our case it will take 4 steps to make the comparison and reach the final value. This is how my successive approximation A to D converter works.